folks. Welcome to Dr. G's What the F Prime lecture series on physics and mathematics. And today we're going to be addressing one of my favorite topics, and that is gravity, specifically Newtonian gravity, or what physicists would like to call classical gravity. And I'm hoping at the end we would touch on Einstein's theory of general relativity. Most exciting. Well, recall that gravity is one of the four interactions in nature. The strong force is the one that holds or binds the nuclei of atoms together. The weak force is responsible for atoms flying apart, or the nuclei flying apart and giving off energy. Then we have the electromagnetic interaction, and these are present in and between charges. So you recall from school, like charges repel, unlike charges attract. And then you have the mysterious force called gravity. It's weak, but it's responsible for the crashing of buildings to the ground and meteorites being attracted into the Earth's atmosphere. It's the same force that holds the Earth to the sun, the moon to the Earth. So gravity literally glues the universe together. I like this little saying, we can't blame gravity for people falling in love. And I think as human beings and creatures of habit, and we're always curious and wanting to understand and put a formula to everything. I'm really happy that we can't put a formula to love. So it gives us something to wake up to, something mysterious, and gravity follows in that same vein. So let's just get on with our study, and hopefully at the end of this lecture, we will throw some light onto this amazing force called gravity. Okay, so to start off our study of Newtonian gravity, let us understand what the man was trying to tell us. The statement of the law is very simple. It says every particle in the universe attracts every other particle with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Wow, that's quite a mouthful and makes one sound really intelligent. But it's important that you understand what the statement is actually saying rather than just learn it in order to obtain marks in an exam. Okay, so firstly, it says that gravity is attractive. Okay, and the size or magnitude of the force depends on not just the masses of the objects involved, but the product of the masses, and it's inversely proportional to the square of the distance between their centers. So just to quickly sum up, it says that the larger the masses of the interacting bodies, the greater the force. And if the bodies are very close together, the force would be large, and as you move them apart, the force should decrease, but it should go like 1 over r squared or 1 over d squared, what scientists would like to call an inverse square law. So the best way of actually understanding the law is to actually pull out a picture. All right, and that's basically what we're going to do next. Okay, so we have our diagram here, which represents two spheres or two masses, M1, M2, and their centers are separated by some distance d, as we see in the picture. The formula for Newtonian gravity is given by F equal to G M1 M2 over d squared. Now, from the previous slide, if you recall the statement of the law states that the gravitational interaction between two bodies is directly proportional to the product of the masses, which means M1 times M2, and it's inversely proportional to the square of the distance between their centers. So these proportionality signs, and there we have an equal to sign, hence we have to introduce a constant. Now this constant is crucial in the formulation of Newtonian gravity and is known as the universal gravitation constant. It has a value of 6,67, if I can get that, times 10 to the minus 11. I'm going to leave out the units for now. I want you to figure out the units. But I want to focus on that 10 to the minus 11. That's a really small number. So even if you're looking at large objects, astrophysical bodies like the Earth and the Sun, the gravitational interaction between these objects is very, very small. Hence, we refer to gravity as being one of the weakest of the four fundamental interactions. I also like to add my piece in there. You know, Newton could have chosen any letter for the constant. He chose G, And why G? Well, my understanding is this is no coincidence. Isaac Newton knew I was coming along to study gravity. Okay, so we're back, and we basically want to now apply the Newtonian formula to solve problems involving classical gravity. So here we have a very simple example. It says calculate the gravitational force between two spheres of masses 1 kg and 2 kgs, respectively, if the spheres are separated by a distance of 100 centimeters. 100 centimeters is actually 1 meter. And so I'd like to encourage you to actually change to SI units before substituting into Newton's formula. But what I'd like to start off with is to identify what's given. So writing down given. If you look out here, we're given the mass, let's call M1. Take that to be 1 kg. M2 to be 2 kgs. What else are we given? We're given the distance d, which is 100 centimeters. Convert that immediately to meters, right neatly. The universal constant is given. Intrinsically, it's there, we know this. So g is 6,67 times 10 to the minus 11. Did you think about the units for capital G? Well, if you think about that very carefully, look at the formula, it's Newton times meter squared per kg squared, like this. What are we solving for? We are solving for the force between the two objects, the gravitational interaction. So if you write down Newton's formula, F equal to G m1 m2 over d squared, and it's simply a matter of plugging in. So G is 6,67 times 10 to the minus 11. Mass M1 was 1 kg, M2 2 kgs, and d squared was basically 1 squared. And then what you do is you whip out your magical machines called calculators or your cell phones, and you start plugging in the numbers. Look, it's so simple here. You can actually use that magic organ called the brain to do this. So 6,67, that should be 13,34. If I multiply that by 2 times 10 to the minus 11, we're solving for the force, so the unit will be the Newton. And there we have it. 13.34 times 10 to the minus 11 newtons. Now this is just the gravitational interaction between a 1 kg mass piece and a 2 kg mass piece. The force is minute. Even for large objects like the Earth, the Moon, the gravitational interaction is pretty weak, as is the case for most astrophysical objects. Also, when you get a final answer, a numerical value, ask yourself, does this answer make sense? Question your final answer. Okay, so we're back with another simple example, and I love the way this is titled, simple. And if you've seen this for the first time, it may not be simple, but things become easier as you practice, and the more problems you do, and the more questions you sort of throw out there, and you probe the theory as well as the fundamental science behind things. This will lead to a better understanding of what you are studying. So here, if you have a look at it, the mass of each sphere is now doubled. Calculate the new force of gravity between the spheres if the distance remains the same. So all we're doing now is just doubling the mass of the spheres. And again, if I write down the word given, so I'm identifying what's given. I'm just going to use a new label, M1 prime. What the F prime? So M1 prime, just a label, is twice the old mass M1. M2 prime is twice the old mass M2. The old M1 was 1 kg, so this now becomes 2 kgs. And M2 was 2 kgs, so the new mass is now 4 kgs. The distance d prime, the new distance, is same as the old distance, and we remember that was 100 centimeters, which is 1 meter. Make sure you write neatly. The gravitational constant G prime is constant throughout the universe at each point, at least for now. And the value would be 6,67 times 10 to the minus 11. Do you remember the units? It's Newton meters squared per kg squared. What are we solving for? Well, we want to look at the new force when the masses are doubled. So we write down Newton's law of universal gravitation for the new force. I'm just going to keep it in terms of these primes, either just labels. And we'll try to write this now in terms of the old masses as well as the old distance. So the two ways of doing it. One, you can simply just plug in the values that you see on the left-hand side, the 2 kgs, the 4 kgs, d equal to 1 meter. Or there's a more elegant way of solving this problem, and this is what I'm going to show you right now. So G prime is G, so leave that as it is. M1 prime is 2M1. M2 prime is 2M2, or double that mass. And the distance d prime was just d squared. So if I multiply out there, I'll get 4 into, now watch this, G M1 M2 over d squared. That's d. If you look at this very quickly, then you look, wow, there's something amazing. The stuff in brackets over here. What is that? That is nothing more than the old force. So what we can write is the new force F prime there is 4 times the old force. So what we've just shown, if we keep everything constant and we just double the masses of each of the interacting bodies, then the resulting gravitational interaction is 4 times the original force. And that's it. Simple as that. Nothing more to it. Another simple problem. Can this get any simpler? Now here, we're keeping the masses constant. So we have the masses 1 kg and 2 kg. But what we're doing now is doubling the distance between the centers of the sphere. So we're going from 100 centimeters, 1 meter, to a distance of 2 meters. Now, if you think of that qualitatively, if we're doubling the distance, would you expect the force to increase or decrease as the distance between the spheres increases? We'd expect the force to decrease. So that is something we need to look out for. So again, just like the previous examples, given the new mass M1 prime is the same as the old mass M1. Nothing has changed. M2 prime is the same as the old mass M2. The distance d prime is now 2 times the old distance. And g prime, we know, would always be constant. We know the value. I can write this down if you want. Times 10 to the minus 11. Remember the units? I'm going to keep asking you that until you learn it. And what we asked to find is this new force F prime. So we write down Newton's law of universal gravitation. We got Gm prime M1 prime M2 prime over D prime squared. And now in terms of the old variables, M1 is prime is the same as the old mass. Masses are constant, but here's the real kicker. It's twice, d prime is 2d, but it's all squared. It's not 2 squared, it's not d squared, but it's 2d all squared. And if you look at that very carefully, if you square that out, then you can write this as 4d squared. And you can write this as g in a very elegant way, m1, m2. That's a d squared. And what's in brackets? And you'll scream out, yay, that looks very familiar. The stuff in brackets. Yes, that's actually equal to F, which is the old force. So what we've just shown is that the new force is a quarter of the older force. As we expected, the force must decrease. So it's actually F over 4. So if we double the distance between the interacting bodies, then the force, the gravitational interaction, is quartered, if I can use that. It's a quarter of the original force. Easy peasy, no sweat. So we're back with an interesting problem here. If you read through very quickly, it says the mass of the Earth is 6 times 10 to the power 24 kgs. It's a nice number to actually know. You calculate the gravitational force exerted by the Earth on a satellite that's orbiting a distance of 200 kilometers above the Earth's surface. The mass of the satellite is given as 5,000 kgs, and the radius of the Earth is given to be 6,400 kilometers. Now, this is a brilliant question, because we've got two distances here. We've got 200 kilometers above the Earth's surface, and we've got 6,400 kilometers from the Earth's center to the surface of the Earth. So which distance do we use? Do we use a combination of them, the difference, the sum, one or the other? And I think this is crucial. Lots of students actually fall short in interpreting the data given and then applying the Newtonian formulation of gravity. So let's just take this very slowly and keep in mind the information that we already have. We've got the mass of the Earth, the gravitating body, we've got the mass of the satellite, we've got some distances, and intrinsically we have the universal constant, capital G. Blink, we are back. Try to remember what we are given. So we have the Earth itself. If you try to draw a picture like that, that's the Earth. And we have a satellite. I'm not an artist, but I'll attempt, that's my version of a satellite that's orbiting the Earth. The distance between, and this is interesting, the distance between the surface, from the surface of the Earth to the satellite, I want to call that distance, let's call it x, and that was given as 200 kilometers. That's not SI units. How do you convert 200 kilometers to meters? You multiply by 1,000, so 10 to the power 3 meters. We are further given, if you remember, the distance from the center of the Earth to its surface, which is what we call the radius. And the radius of the Earth is, let's call it R subscript E, was given as 6,400 kilometers. Convert that to meters, you get 6,400 times 10 to the power 3 meters. Right, interesting. Go back to the formulation on slide 2 of what the statement of the law was saying. The interaction between the two objects is inversely proportional to the square of the distance between their centers. So would you use d equal to 200 kilometers? Would you use d equal to 6,400 kilometers? Would you subtract the two, or would you add the two distances that are given? Right, we are further given, think about that, the masses. The mass of the Earth, right, is capital ME. That was 6 times 10 to the power 24 kgs. The mass of the satellite, let's call it MS, was 5,000 kgs. And by now you would have figured this out. And the distance we're looking for is that distance x plus RE. So 6,400 times 10 to the power 3 plus the 200 will give me 6,600 times 10 to the power 3 meters. Now, do not go on if you don't understand why we're adding the two. Remember, it's the distance between the centers of the object. So from the center of the Earth, not the surface of the Earth. And capital G, we already know, is 6,67 times 10 to the minus 11. And if you look at the units, it's Newton meters squared kg minus 2. You notice this is my fourth example that I'm doing here during this lecture, and I keep writing out the value of G. And I think it's important to do that. So you get a feel for the number. You also get a feel for the dimensions of the units for G. What are we looking for? Well, we want to solve or find the force between the Earth, or the force that the Earth exerts on the satellite. So we write down the Newtonian formula, F equal to G. That's the mass of the Earth, mass of the satellite, divided by the distance squared. So that'll become 6,67 times 10 to the minus 11. The mass of the Earth 6 times 10 to the power 24. Mass of the satellite is 5,000. And the screamer here was this, and this is where a lot of students make mistakes, was the total distance times 10 to the power 3, all squared. And you would use either your trusty old brain or your calculator to actually work out this answer. And your final answer will be in newtons. And there we have it. Simply done. Straightforward. Just keep recalling what we did to the distances involved. Very, very important here. It's the distance from the center, not from the surface. Okay, so this is a really cool example, and that is, you're looking here at launching spaceships towards the moon. We have people that still believe that we haven't been to the moon yet and that we live under a dome. That's interesting. Why do you have to accept everything that's in our textbooks or what our teacher tells you? It's good to question, look beyond, and even formulate your own little theories. Name laws after yourself. Wow, that's amazing. So anyway, on a more serious note here. So it says here, in our quest to conquer space-time, we attempt to send a spaceship towards the moon. And we want to establish a base on the moon. Now, why would we want to do that? As the spaceship heads towards the moon, something interesting starts to happen. Obviously, the Earth will attract the spaceship towards itself, and the moon will attract the spaceship gravitationally. So if you look at these objects in isolation, there's an interesting problem. It's like a three-body problem, but it's not as easy as that. But we'll try to simplify things. So we have the Earth, as you see in the picture here. We have the spaceship that's moving along, and there's your little moon over there. So Earth's going to attract spaceship, Moon's going to attract spaceship, and at some point, what the question asks is, there will be a distance at which the force that the Earth exerts on the spaceship would equal to the force that the Moon exerts on the spaceship. Force that the Earth exerts on the spaceship must equal to the force exerted by the Moon on the spaceship. We're speaking gravitationally. Calculate the distance at which this will take place. And a lot of people, the misinterpretation and the misunderstanding of physics would say, if these two forces are equal, then it's like a tug-of-war, and it's proof enough that no spaceship could ever reach the moon. My, we've got to think about what we say very carefully. It's like when you ask people, why is the sky blue? What is the immediate answer? It's the reflection of the sea. Oh no! That misconception has been around for many a year, and it has to change. It cannot be the reflection of the sea. There's more to that question. Anyway, let's come back to the Earth, the spaceship, the moon. We're living under a dome, and we've never been to the moon yet. Okay. Back, so what we are given, if we now want to write down, let's look at the Earth and let's look at the spaceship. Okay, so the force that the Earth exerts on the spaceship would be capital G, mass of the Earth, mass of the spaceship. And let's just say that the distance between the Earth and the spaceship is going to be x, so that should be x squared. But let's just look at the three-body problem. So if we just stick to this, there's the Earth on this side, there's the spaceship here, and there's the little moon over here. If the distance between the Earth and the spaceship, the centers, let's call that capital D, and the distance between the Earth and the spaceship at which these forces are equal is x, then you must agree with me that the force exerted by the moon on the spaceship would be capital G, mass of the moon, mass of the spaceship. Now, what would we put for distance? Would it be D? Would it be x? No, it's the distance between the moon and the spaceship. Sorry, that's spaceship. So if the total distance is D, and we have chomped up, I've eaten up a little distance, x, so what remains for the moon spaceship system is d minus x. So this becomes d minus x, but not just d minus x. What Newton said, it's all squared. So when these two forces are equal, what do we have? So we have g, mass of Earth, mass of spaceship, over x squared must equal to g, mass of moon, mass of spaceship, all over d minus x all squared. And something incredible happens here that gives you goosebumps. Capital G disappears. The mass of the spaceship cancels out. We know the mass of the moon, we know the mass of the Earth, we know the distance between the Earth and the moon, and we can easily solve for x. Brilliantly done. But you may sit back and say, oh my goodness, if the mass of the spaceship cancels out, then something very interesting happens. It tells you that this distance x, which the force that the Earth exerts on the spaceship equals the force that the moon exerts on the spaceship, is independent of the mass of the spaceship. So if the spaceship was a little jelly bean, or it was as large as the Hadron Collider, that distance x would be the same. Don't you find that fascinating? Think about that. Go to bed sleeping with one eye open. Yes, you know, we live in a world where the selfie has become some instrument or gauge of popularity and people being loved or being felt like they're being loved and all sorts of things. So people are on a massive campaign on looking good, just that outward appearance. Okay, there are some for health reasons, but also get on to what we would call a weight loss program. But more importantly, I think we know as scientists, physicists, students of physics, that it's not really weight loss, but it's mass loss. You see, the mass is just the quantity of matter that makes up the object. It's the atoms, the molecules, the stuff that you're made up of. So what is weight? Well, weight is the gravitational interaction, say, between yourself and the center of the Earth. And we'd figured out, following Newton on this one, that the gravitational interaction of the force goes like 1 over d squared. And I think I did mention to you that it's known as an inverse square law. Okay, so if you had a plot force versus distance, then you get this beautiful red curve, which basically means as you move away from the gravitating body, like from the surface of the Earth, and you move into orbit, the force drops off very quickly, like 1 over d squared. So if you triple the distance from the center, the force will drop off as 1 over 9. 4 times the distance from the center of the Earth as you move out into orbit, it'll be 1/16. So yeah, so I think it's important to educate people and say, okay, yeah, it's not weight loss, but really mass loss. But then they're going to argue that mass is connected to weight. And we know this from a very simple formula, that the weight of an object, W, is equal to m times g. Okay, where m is the mass of the object and g is the acceleration due to gravity. And close to the Earth's surface, g is approximately 9,81. Schools use this as 9,8 to 9,81 meters per second squared. Notice that it has the units of acceleration. So bodies falling under the influence of gravity alone will accelerate close to the surface of the Earth at 9.8 meters per second squared. Now, to calculate your weight is very simple. If you're 100 kgs, the stuff that you made up of, multiply that by 9.81 meters per second squared, and that will give you the weight. And since weight is a force, your weight would be measured in newtons. So 100 kg mass would weigh 100 times 9.81, so that gives you 981 newtons. So on the surface of the Earth, 981 newtons. Take this person further out into space. His weight's going to decrease. It's going to be getting less as we move further out, but his mass cannot change. His mass will still be 100 kgs. Excellento. So we just mentioned the weight versus mass, and we've come across little g, the acceleration due to gravity. So how do we calculate that? Well, we know that the weight of an object, W, is m times g. We can also calculate the weight of the object from the Newtonian formula, which is capital G. The Earth is actually the gravitating body, mass of the Earth. That's attracting you, which is your mass, little m. And it's divided by the distance between yourself and the center of the Earth. So that d also takes on a special form, because that d turns out to be the radius of the Earth. So we can write this as g, mass of the Earth, mass of the gravity body, divided by the distance of the radius of the Earth squared. So have a look at this very carefully here. We have a formula for weight, and we have a second formula for weight. And so we equate them. mg is equal to g mass of the Earth m all over r squared e. The mass of the gravitating body will cancel out in that way on either side, and we got a formula now for the acceleration due to gravity close to the surface of the Earth. So it depends on the universal constant capital G, the mass of the Earth, and of course the radius squared of the Earth. So this is for, let's put a label here, the acceleration due to gravity close to the surface of the Earth. What do you think the formula would be for the acceleration due to gravity on the moon? Bearing in mind that this is a universal formula. So the gravitational acceleration on the moon will be g moon capital G, the same form. But we speak of the moon, not of the Earth. We speak of the radius of the moon. And there we have it. So if we know, for instance, the mass of the moon, which we already know, we know the mass of the Earth, we know the radius of the moon, and we know the radius of the Earth, we can calculate the gravitational acceleration on the moon. So look at this formula. Let's call this 1. Let's call that 2. Now try this as an exercise. Take formula 1, divide that by formula 2. Don't rush it. So 1 over 2, so you got GE over GM. And if you play around with this a bit, you can see the capital G's will cancel out. And then you'd have something like, okay, let's just do this very slowly so that nobody is confused. That's 1 over 2. Right, so you don't have to be a rocket scientist to realize the capital G's will cancel out. And if you simplify that very carefully, you'd end up with me over r squared times r squared m over mm. The right hand side, all the quantities are known. The mass of the Earth, the mass of the moon, the radius of the Earth, radius of the moon. So we have a ratio of GE over GM. But we know the acceleration due to gravity on the Earth is 9.81 meters per second. And when we complete the calculation, we conclude that the acceleration due to gravity on the moon is approximately 1/6 the acceleration due to gravity on the Earth. And that is no surprise because of the compactness of the moon. And obviously, its low mass as well. So that's a cool calculation. This is one of the most exciting slides I've come across. I mean, what we've been through up to this point is very interesting, and Einstein's gravity would not exist if it wasn't for Newtonian or Newton's formulation of gravity. You know, we just build from one theory to another. And, we speak of gravity being attractive. And there are very few people that actually ask, can gravity be repulsive? Now, this attractive nature, and if you look at Newtonian formulation, it seems like there's something happening between the two bodies. There must be something carrying that force, or there must be an exchange of information between the two objects for them to attract each other. But Einstein's picture of gravity was revolutionary, and it's very, very interesting. And if you Google this, they'll always give you the picture of, think of a trampoline with no one standing on it. It appears flat and it's smooth. You take a big ball bearing or an object and you place it in the middle. So the entire trampoline now sags inwards towards that mass piece. So that's what Einstein called the distortion or curvature of space-time. So a massive object, like the picture you see or the animation you see, a beautiful animation, this. Thank you to the creators for this beautiful animation. You have the orange object, which basically is the sun, sitting in empty space-time and then distorting the space-time close to it. Now, if you look at the lines further away from it, the distortions just get less. And interestingly enough, if you look at the green object as it travels in orbit around the bigger object or the sun, what it's really doing is it's moving in this curved space-time, which is very interesting. And here you have in all its glory what we call the Einstein field equations. Okay, so the left-hand side here represents the geometry of space. And the right-hand side represents the matter content of space. So the type of matter that you're sitting in here. So for instance, this picture, the matter here would be obviously the sun and the Earth system. And the left-hand side is the geometry, which basically tells you the curvature of space. And in Einstein's theory of general relativity, it's matter that tells space-time how to behave. It's a really interesting, beautiful concept, very difficult to grasp as well, because we're looking at a four-dimensional theory as opposed to the standard Newtonian gravity that we all speak of. What's interesting about Einstein's theory of gravity is that in its weak limit, the weak approximation, it does reduce to what we call the Newtonian limit, which is the physics we study at school and in undergraduate university physics courses. So I would appeal to you, if you're excited about this stuff, you want to think out of the box, you want to go to higher dimensions in terms of understanding theories or just picking your mind or your brain, just Google the theory of relativity, starting off with Einstein's special relativity, and then surely and slowly make your way through general relativity, not getting caught too much into the technical details or the mathematics, but just trying to get a quantitative feel for what curvature is, four-dimensional space-time continuum, all these beautiful words. I mean, the mind's a beautiful thing. Let us not waste it.